Now let's look at the lift system. Okay, so this lift base, and this is starting on it. Okay, this is our lift base. This is the lift. Okay, now the lift is what is registering. This is what registers the weight on the scale. So the lift is registering the weight of the scale. So the force that is felt, the force that this lift, the upward force that this lift felt is equal to scale weight. Okay, where the scale will say as the weight. Okay, so we can say that that force that this scale is recording is what is actually going to appear as your weight. Now, when you stand, let's look at the forces in action. When you stand on the base of the lift, okay, your standing alone is giving us your mass as times gravity as the force. Okay. Now this, for every force, there's equal and opposite reaction. So the lift also exerts an upward force. Let's say F normal, because that's the normal force. F normal. Okay. Good. So if we look at this in the Cartesian curve, let's say this is the y, this is the positive y. Okay, when you're coming down, it's negative y. Okay. So that you see that your weight is coming with this mg, and then this is also coming, the reactional force is Fn. Okay, so it's a resultant, which will tell. From these two, we're going to have a resultant force. Okay, but remember that it is the normal, the reaction of the lift, the reaction on your soul, or the reaction against your soul. Okay, this, the reaction against your soul here, is what registers on the scale as your weight. Okay, that is the concept I want you to take. So we can see that from here, you can set up an equation for this scenario. Your body exerts mg downwards, and then the surface of this lift base also exerts a force Fn against your feet. Okay, and then the two forces will come out with the resultant force. So this is how the equation will be. If we assume that the one going in the direction of positive y is positive, so we have positive Fn, that's the normal force, and then the gravitational force, the weight of the body is also going down. It's against, it's not in the direction of the positive y. Okay, so that will become negative mg, and then we'll have the resultant depending on. So this can come, this lift that you see, the lift base here, can go with any acceleration. Okay, can go with any acceleration, just as, but the body of the body of the person is always mg, right? It's acting downwards, it's always mg. Now, so the resultant is going to be, let's say, ma, setting a. Okay, ma, setting a. Right. Now, this is what registers on the scale as your weight. Okay, so when you have this, we can more or less solve almost every question. Of course, in this one, we can have, let's say, the mass of the lift times acceleration or something, but not the same mass, another mass. Okay, times this acceleration, so it's going and all that. Then this acceleration can also, but let's call that Fn for simplicity's sake. So when you have this scale like this, so this is the net, the resultant force. Okay, so if you are told if the lift is exerting Fn and the mass is this, the resultant movement of the lift will tell you this one. So this is the resultant, whether it's going up or down. Okay, right. So you realize that if Fn, let's say at rest, if the body is at rest, okay, at rest, it's not moving. See that the net acceleration here will be 0, so it's going to be m times 0, and then we have mg, fn, so this is going to be 0, and then you have fn minus mg, so that fn is equal to mg. So when the this lift is at rest, the normal force against your feet is equal to your weight. Okay, mg. Okay, so at rest you will get your normal weight. Okay, now let's see if the lift is let's say the lift is going downwards, okay, with a certain acceleration. So Fn minus mg, let's say the lift is going down with a negative acceleration, depending on how it's going. Maybe the acceleration is it's going down with acceleration 12 meters per second. This is more than what? Times 12 meters per second. This is more than acceleration due to gravity, which is about 10 meters per second squared. 12 meters per second squared is less than that. Okay, so in that case, you see that the Fn here, this will cross. Already we have something times 12 here, so we have m times 12 here, plus mg. So what do you think the weight will be? If the body, and of course we are saying it is going down, like that. If it is going down, you can look at it. If it's going down, then this acceleration is going to be negative, so it will be negative here, and this is going to be positive. Okay, this is already, it was negative, so it becomes positive here. But you see that because it's negative here, the final result is going to get a negative. If you are going to get a negative value here, it will tell you the weight is going to register something less, so you will feel weightless. Okay, in that sense, because this is going to be negative, because acceleration is negative here. Okay, and this is your magnitude mg, right? Your mass, and that is already in there. Okay, so that will give you a negative value. So the negative value means so when the lift is going down with an acceleration which is greater than 10 meters per second squared, okay, then you are going to feel weightless. Okay, now let's see the opposite. If it is going up with acceleration which is positive, okay, it's going down, up, like that. It's going up in the positive direction. So in that case, the acceleration that we're going to give, or let's say the method I'm going to use. So if it's going up, okay, that's positive. So this side will be positive. It is Fn here. So this is going to be positive value, and of course this is also going to be positive. So what do you think will happen? So if it is moving upwards with the acceleration greater than acceleration due to gravity, then your answer is going to be positive. Okay, the answer is going to be positive. So positive means you feel what? Heavier than you feel yourself. Okay, you feel heavier than you feel you are when you are at rest. Okay, so that tells you. So from here, when it's this way, here is negative, here is positive. So you can have a negative value or near zero value. Okay, so this will explain why in the lift you can feel heavier or lighter, or not feel like you have normal weight. All will depend on this manipulation of this equation. Remember, we made a setting for this calculation. We said we chose the positive y direction. So if you are going there, it's positive. If you are coming against it, it's negative. Okay, we didn't look at the sense of gravity as if you are moving in the direction of gravity is positive. We didn't look at it that way. We chose the graph kind of equation to solve this. So you can use the same thing to solve that, right? Now, so the point you should note is one. If the body is the lift is moving with constant velocity, it means there is no acceleration. And if there is no acceleration, this becomes zero. At that point, what? Fn becomes equal to that. So you feel your weight as it is. Okay? So the point I want you to notice, when there is constant velocity, usually there is no change in sensation. Okay, but when there is a change in velocity, then there's a change in sensation with respect to weight. Okay, right. So that is that. Now, if the body is moving with the same acceleration as gravity, what do you think will happen? This is also mg. Let's say this is also mg. Okay, this causes becomes plus. Okay, and then it depends on whether it's going up or downwards. Okay, so if it's going, let's say upwards, then this is positive. This positive becomes positive. If it's going downwards, it's negative. This becomes positive. Then it cancels out, so that F becomes what it says 0. Then you are weightless. Okay. So if the lift is moving downwards acceleration due to gravity, it's more or less like saying that as the lift is going down with G, you're also coming down with G. So there's no sort of normal force against your feet. So you feel what 0, or you feel what weightless. So that is the principle for this one. Okay, right. Now let's look at the escape velocity. That's the next thing we are looking at, escape velocity. So this is the surface of the Earth. Then we have a rocket that we have here to be fired. Okay. Now this is fired such that it escapes the force of gravity. We want it to escape the force of gravity. So that's rocket for you. Okay. Sometimes we can fire satellites into space to orbit us. Okay, so fire it here to orbit us. We're going to look at that. So it will be revolving, going around us, monitoring us at a certain point, and it is also a certain height above the surface of the Earth, and this is supposed to be fired so that with the velocity such that will make it escape the attraction of the force of the gravity force of the Earth. Okay, so that's a rocket. This satellite here. We look at the two together. If we consider, let's see. If we consider, let's consider this one is a rocket. Let's say this is another satellite. Okay. Let's consider this. Right. Now let's see what happens. Let's first deal with this rocket. Right. Now this rocket is being fired. We want to fire it such that it will escape the force of attraction of gravity. Now then it means we are firing it to infinity. We are firing this rocket to infinity. Of course, remember the rocket obeys the third law of Newton. For every force, there's an equal and opposite reaction. And also obeys the momentum, conservation of linear momentum. So if a body, if you are losing mass, of course, that should be accounted for, you move in that the opposite direction. Okay, that in itself. So the force of gravity, the third law of Newton, and then the relation to momentum conservation, linear momentum conservation comes in here to explain how the rocket is able to go to space. Okay, so we are firing it here from here to space. Now we want to find the escape velocity. We want to find an equation for the velocity. Now if we are firing it from here to here, the energy that we will need will be equivalent to the potential energy here, the potential here, and the potential there. Okay, so the potential difference will give us the potential. If you multiply by the mass, it will give us the energy that we need. So we know the potential, by a body, potential for a body is what? Negative G M R. Right? You can do the deductions and then get the answer. So there is a small m. This is because we know potential is equal to, you can just work it out. Work done. So it's what potential is equal to work done over what? Distance. And now work done is force times distance. Okay. So we can easily deduce it. Okay. I'm just trying to derive it. Okay. So that G, our force is G M N N over R squared times this distance, which is R. So we divide it by R. Okay. Of course, work done, that's the force times the distance. Okay. And distance. So this will cancel one out, this cancels that. going to get r squared. So that's going to be Gn, and that is going to give us the. So yeah, let's see. Okay, so okay. Sorry, I think this is where we made the mistake. This m. So the potential is work done per mass. Okay, work done per mass. Okay, sorry, m here. We have our m here. Okay, so this is going to reduce to what r. So you're going to have what? This m is going to cancel Jm over r as your potential. Okay. Remember we said that intensity is force per cube or force per mass, and then potential is with respect to work done. So work done per cube or work done per m, depending on the body you are dealing with. So this is what you have to use that to get that principle. So voltage, the potential is this. Now if you, the potential of course is the work done per mass, moving it from one unit to the other, okay, by definition. Right. So this is the potential. Okay, this is the potential at the point. The potential at the point is negative because we use infinity as reference point. So potential anywhere will be less than the potential at infinity. Okay, so if you want to find the potential at that point, reference to, so it means it is going to be infinity potential minus potential for that body, and that becomes minus V, and that is why this is V minus. Okay, so this is the potential that we have. Now, what we have to do is we should know the potential here at the surface of the earth, and then the potential at infinity. Potential at the surface of the earth is equal to negative J m over r resistance, okay, of the earth, okay. Right. That is it. Right, so that is the potential here. The potential here is 0. So if we want to find the energy, it will be the energy will be equal to what? Mass times the potential. The potential, okay. And this will mean m times into bracket. Let's find the potential. The potential difference will be the energy. So that will be 0 minus into bracket minus. What is the difference? Okay, the difference. So we are subtracting, but already this is minus. So G and RE. Okay, and this is going to give us what? It's going to give us positive J M E R E. Sorry, R E. So this becomes the energy. Now this energy that we have between the two, if the rocket is able to go to infinity, that will be the energy that would have been used, okay? But it's going to move with the kinetic energy, okay? So it's going to start with the kinetic energy. By the time it gets to this point and stop, all the kinetic energy has been converted to the potential energy here. All right. So that kinetic energy that it's moving with is given by what? Half mv squared, okay? mv squared, okay? It's given by half mv squared. Now the point is, of course, starting with a certain velocity, initial to the final v, so 0 to final v, okay? And before that, before it stops, okay? Right. Somebody also say started with v constant or whatever. That's the point. But the point is starting from 0 to the final v, because it will start and then be increasing. So we want the minimum velocity that the rocket needs to move with so that it can escape the force of attraction of the Earth. So having said this equation, this is the equation that we're going to use to find the escape velocity. So this velocity that is in this equation will be the escape velocity, will be the minimum velocity that the rocket should have to be able to escape the attraction of the Earth. Okay, so let's see how that will work out. So from here, I'm going to have what? G M R E is equal to half m v squared. So this m will cancel this. Okay? Right. And then we're going to have, let's rearrange. We're going to have 2gn is equal to this times that. That's going to be what? Re times v squared. Let's write it as v squared. Re is equal to 2gn. And then from here, making v squared the square, this subject is going to divide 2gn over Re. Okay? Right. So here, we have to find square root of that, and then square root of this. So that v is equal to square root of 2gn over Re. Right, so you see that this is what we call the escape velocity. That's the expression for it. G is a constant, the m2 is given to you, and then the radius of the earth is also known. Then you should be able to find the mass in this equation is also given to you. Then you should be able to find the escape velocity needed. Right. So in this case, is the earth between the earth and the second body, which is the unit mass. So the m will be given to you as the mass. Okay, so once you know the mass, the earth mass, the g, gravitation due to gravity, acceleration due to the gravitational constant, that's g, capital G. You know 2 is there, you find the square root of 4 there. So the square root of 4, okay, and then you get your escape velocity. So let's see how it will go. So if the escape velocity, if it is high, then it's going with the hyperbola. It will go, if it's far above the escape velocity, as a hyperbola type of curve is gone. Just when it is v is equal to the escape velocity, then that will describe a parabola curve. Okay? Now if it is less than the escape velocity, the velocity that rocket is supposed to be is less than, then it will end up having an elliptical curve. If it is far less, then it will have almost a circular curve. Okay? And that is how it's going to be. Right. So let's clean and then see how we can also get something for the satellite. So you don't need to commit the formulas into memory. You can easily derive it, like we went through. Okay, so let's see now the same Earth surface. This is our Earth. We want to launch it into space. This our satellite. We launch it here. So we're going to go with kinetic energy. Then when it gets here, it has potential energy. Then once it's here, it's also revolving around the Earth, so it will have another kinetic energy. Okay? Right. So it's a matter of adding equations. Let's see the total energy this will have. The total energy it will have when it's moving with kinetic energy. At each point, part of the kinetic energy becomes potential energy. So at this point, when it stops, when all the kinetic energy becomes potential energy. So we'll have potential energy here. Now once it's here, it starts moving with another kinetic energy. So plus that kinetic energy in its power. So that will be it. Now how do you get the potential energy here? Your potential energy, we can get it, okay? If we know the potential between the two, if you know the potential here, if you know the potential and we multiply by mass, the unit mass, we should get the potential energy. Then of course we do kinetic energy, it's half mv squared. But of course this is moving in a circle, so the expression can be given in the form of angular velocity. When you know the radius and all that, then you can use that to work things out. Or we can find an expression which can convert this into the gravitational equations. Then we can have that. Okay, so let's see. Here, potential energy. The potential energy here, that is what we have there, will be the one here, the difference, okay? So here minus that, this negative, this more negative. We have negative Okay, let's say negative this P, let's say P2, P1, so that we have the potential here P2 minus P1. Okay, so that is more energy than this one. Okay, with reference to this, we are saying if you are further, like the infinity is 0, so the one infinity has more potential energy, so let's have things like this to have more potential. So that one is given by G M. The potential is what Gm R. R will be the radius. Radius from this one. This one. Let's say R. R okay. This minus the one on the surface of the earth is also going to be Gn R radius of the earth. Okay. So that will be, this is going to be the potential. So what do you think is going to be the answer? So this is the total potential we are looking at. Okay? Right. This we can also say R1, where R1 is the same as R1. Okay? Let's simply see. Okay. Right, so from here we're going to have negative, this is going to be positive. Okay? That we have. Okay? Gm out. Okay, then we have our so this is going to be M out 2 plus what Gm out E. That's the total potential. Okay, and then this is the total potential. This is the kinetic energy. Of course, you can express the kinetic energy in terms of omega this, then you can use that one to also do that. Okay, but the point is the total will be potential energy plus kinetic energy. But remember the expression for kinetic energy here in this case. Okay, right. Alright, so this will be an expression for the total energy for the satellite as it moves in this orbit. Okay, kinetic energy and potential energy plus its kinetic energy. That's something we right, so that is that. But so let's remember potential energy. So this is an expression for potential. This is the potential. So the potential energy we have to multiply by the mass. So it's potential times mass. So this times mass. This times mass. Okay. So this will be this. This will be that. Okay. Right. So that's energy. If it were just potential, then the expression holds. Right. So let's look at something to here. Now, as it is, we can relate this circular motion to the force of attraction between the two bodies. The force of attraction between the Earth and the satellite will be given by, the force of attraction will be given by G, and this is the satellite, that's the satellite. And then the distance between them, okay, the distance between them will be what your R2, right? Be R2. Okay? Now, this force of attraction between them will also be equal to the centripetal force this one is experiencing towards the center. What is holding it? It's the same force that is also the force of attraction. Okay? Right, so that force of attraction is also equal to the centripetal force, which is given by mv squared over r2 here. Right? Okay. Now, if we look at the two from here, we can say that G and R2 is equal to mv squared R2. Okay? So what happens? This can cancel that. Or in other words, if you look at it carefully, so you can leave it as that and then just see how this can be related to kinetic energy. Kinetic energy is equal to half mv squared. Okay? We have mv squared here, so mv squared here. So we can try to find an expression for kinetic energy in terms of this. So let's see, from here, v squared will be equal to what? You can put it there and see. V squared will be equal to, if you put v squared there, that's what we're going to have. V squared will be equal to this, we cancel that, so it's gone. this is so v squared is gm. Gm actually. So this becomes gm squared, and then that gives you an expression for kinetic energy. And then you can look at it, you can compare that with what you have here. Right. So let's get it well. Okay. Right. So from here you can see that it implies that v squared is equal to gm. Okay. So you can do that. So the point is, just get it first. The total energy will be the potential energy of this mass, potential energy at this level because of the height, and then the kinetic energy is given by this. Okay, if you want to find moving from here to the energy that has been spent, that will be the difference for this one. Okay, but the energy, the potential energy in this is given by just this expression, this here. Just take note. So this is not the total. This is it. This alone is for this. Okay, because that will be the potential energy here. But if you want the energy between from here, moving from here to here, you can subtract the potential energy here from here, and then that will give you the energy in between. Okay, it's in between, but the energy at this level is this level. Okay, the kinetic energy is given by that. V squared said is gm. So if you put gm here, you're going to have what? Half g capital M this over what? Where is it? So gm, we put it here. Where is our m? This 4 squared to this over that. Okay, so v squared, if you put gm here, of course there's you have there. If you put it there, then you are changing the equation. So let me put it this way. Let's work it out here. V squared is equal to that. Now this is it. From here, v squared is equal to gm, like we have calculated it. Gm. Okay, so if you do substitution, if you put it in this equation, you can work it out too. Right, so let's see what happens. Sorry, we didn't put our square here. This is square. Okay, this is square, but this is not square. Okay, so if you look at the two, this is going to be square here, right? So this is going to be v is equal to gm over r. That is gm over r. Gm over r. So if you put that one here, you're going to have, if you put it here, you're going to have half m g m over r. Okay, this is the expression you have. And then for potential energy at this point is given by negative g m over r, which is the radius that it has from the surface of Earth. Okay, that radius has the potential energy. So it's potential energy. So it is your this divided by your per mass. So that becomes your what do I do? Here, and then you have. So if you look at this one.